Hello, everyone. This is the iDesign team presenting three core functioning units and the entire RV32I core running a simple program. We're going to start with the instruction fetch unit. This is just a simple test bench right here. We have a list of instructions that is being pulled by our fake memory, which is located right here. It pulls from a file, and then it'll be sent to the cache, and from the cache, it'll go to the iFetch unit. In the iFetch unit, we'll compare the expected instructions with the actually fetched instructions. So we'll run the simulation. In the simulation, we see signals from the fake memory, the iFetch, as well as the dcache. And we take a closer look right before we get actual instruction retrieval. We have a no-op right here and a program count here as well, a 0 program count. As you can see, we have the instructions incrementing. We have this is the third instruction and it matches. Here it matches as well. And it gets all the way to our 8 instruction right here as well. Here's the log. As you can see, this is the program counter, the fetch instruction, the expected, and they all match. With that, I'll give my time to Nick and he'll talk about the decoder.
Hello. So after our instruction fetch, we have to send our data over to the decoder. And here I have a test bench that we use on the Cadence Excellium servers. And this pretty much is the interface between the instruction fetch and the decoder. So in this test bench, we make random values for our program counter and our instructions, and we just make sure that gets to the decoder correctly. So this is another way of testing out our modules. Instead of just making tests ourselves, we put applied random pressure. And so to run this, I just run the top file and Excellium will build, but it won't give us a waveform. So that was one of the issues we were having and why we're using Vivado for most of these tests. But as you can see here, we finished the simulation without bugs. And that means there was no mismatches between the instruction we received and what the decoder was reading. Before we had a little bit of trouble with that. And so next I can move on to letting Pablo talk.
Yep, thanks, Nick. I'm going to show you all a test bench for the underlying cache implementation. So we can see that we have the cache implementation as well as a fake memory module that acts as a top-level RAM for simulation purposes. So let's run the test bench and we can see that the first operation that the test bench performs is to write a word to the hex address 8000. We see that because this is a compulsory miss, the cache first has to retrieve that block from memory. The next request from the test bench is to read back that data that we have just written, and we can see that it returns the data exactly as it was originally sent. Now let's try a capacity miss in which a block that will lie on the same cache line as the previous block will be sent a cache request. This means that a miss with a dirty block occurs on the cache, and the cache sends the dirty block back to the fake memory and reads the appropriate block. And we can see here that we just get zeros because that's the default value for a memory. But now let's try reading back the original value, which again causes a cache miss, meaning that the cache has to retrieve the block from the fake memory. And we can see that indeed the cache misses and misses on dirty blocks and the write back work properly. Now I'm going just to show you how the cache, how it is possible to write less than one entire word in the cache. In this case, we are going to write to this memory address an entire word. The next subsequent request is going to write only the top half of the word. So it's going to overwrite the first half of the word, but keeping the the bottom bits of the word exactly as they were before because of this write mask. So when we see that after we send the write request, the next request is indeed returns the top 5 bits that got set because of the write mask, as well as the bits that were not included in the write mask were the same one as the previous operation. So this means that writing to the cache using a write mask to mask out which bits to write is also working properly. So thank you. I'm going to now pass it on to Yusuf.
Yusuf, you're muted.
Go.
Hello, this is Yusuf. So I'll be showing you guys today the Fibonacci program running on our right CPU. But first, I'll show you it's running on a different processor so you can confirm the results are accurate. So this program completes a 20th iteration of the Fibonacci sequence. And you can see the results are here on the register file. And now we can try this on our CPU. So this has the program already loaded, and we're going to run it. And as you can see, if we zoom in on the register file, you can see the values match on both register files. And you can also see the instructions getting loaded in the instruction stream. And this is our files that we're using for the simulation, which is basically all modules in the CPU. And if you look at our RTL schematic, you can see all modules being in use. It's specifically and especially the forwarding unit where it connects to the memory unit and execute on a decoder to correctly forward the data to avoid data hazards. And with that, and one last thing is that we also computed our MIPS rate that the frequency we need to hit 100 MIPS, and it turns out it's around 120 megahertz for this architecture. And with that, I'll go back to Brandon for the conclusion.
Yeah, guys, so for more information, definitely take a look at our GitHub. What we presented is basically 3 functioning core units as well as our entire core. We have multiple more modules in the GitHub as well as our old core. So take a look at that, and thank you guys for watching.